Today we're going to talk about host-side memory model. In OpenCL, both the host side and the device side have memory spaces we can use to store data and perform computation on them. But OpenCL specification has few specific requirements how we allocate data and how we move them. We can conceptualize the reading and writing of buffers and move data to and from the device, but these are actually not explicitly required. We have different ways to ask the OpenCL framework to allocate memory spaces and move data. The memory management examples we're going to see attempt to show you that some of the subtleties of real implementations. We know that the devices operate with memory systems that are often separate from the main memory on the host side. We're going to start today to talk about the host side memory model, where we can use that to provide ways to better utilize the memory spaces on the host and on the device side. The OpenCL host side memory model supports a so-called relaxed consistent model, where the global synchronization of memory is defined only with the completion of events. Some newer OpenCL specifications have optionally consistency guarantees as in high-level languages. But today we're going to focus on the majority of these relaxed consistency model. We're going to look at some examples of memory object creation, and we're going to show you how to use memory flags to define or specify how we want the data to be allocated and how to initialize them. We're going to show you examples of writing and reading buffers and how to manage these buffers, in some cases migrate these memory objects. Also, we're going to show you how to use host accessible memory. We talked about memory objects in the past. The memory objects are the instances that we use in a context to work with data. Oftentimes, we want to provide synchronization among these memory operations, and we use, for example, wait for events, which is a little bit different from a marker, which this is really not an event. These events are in the queues for device, and these devices will take different memory operations, put it into the queue, and perform the corresponding operations. And the memory objects host the execution of queues for a specific set of triggering events that have completed. We're looking at here three types of memory objects, and mostly we're going to look at buffers in this lecture. Although we have touched upon image object in the previous lectures, pipes is something new in OpenCL 2.0, and we're going to spend a dedicated session on that. Buffer objects in general are one-dimensional arrays in the traditional CPU sense. You can use buffers for initializing your data, and also for computation, and of course for storing the computation result. It's similar to malloc, use the C program, but we use create buffers in very different ways as in a C program. Buffers can contain any scalar type data, vector data, or user-defined structures. Images are dedicated buffers designed for accessing image data. So the data in the image objects follows specific format so that the image-related operations can be performed very efficiently. Pipes are used to organize data in a first-in, first-out FIFO structure. We can pass data from one kernel to another kernel. But again, today's lecture, we're going to talk about buffers exclusively. We can use different memory flags when we create buffer and when we operate them. Moving data at runtime is inefficient. So OpenCL attempts to provide options as part of the commands to suggest where the data is allocated and when and where the data should be moved. We used CL Cre Buffer API to create a buffer object. And this table lists the memory flags that we can use to define the attributes of the buffer object. We're going to go through this table very briefly, and we're going to show you examples later. So we can see this table has memory flags, and the first three memory flags are somewhat familiar to us: read, write, write only, and read only. These three memory flags are used to specify the types of access that are allowed by a kernel. And note that the memory object is used primarily by the kernel. The next few memory flags, for example, CLMem use host pointer. This use host pointer is to tell the OpenCL runtime that we're going to use a host pointer as the storage for the buffer. So the buffer is going to be allocated in the host memory space. Although in real implementation, the OpenCL depends on the vendors, the device can choose to cache the content to device memory if it turns out to be more efficient. And then kernels can use the cached copy on the device when a kernel executes. The next option, CLMem allocate host pointer, is to allocate buffer storage in the host accessible memory. Note that we are trying to allocate buffer, and this buffer is supposed to be accessed by the kernels executed on the device. Allocate host pointer is to allocate buffer storage in some space that is accessible to the host. If the OpenCL runtime allocates the buffer on the host memory, it is certainly going to be accessible to the host. If the OpenCL runtime determines to allocate the buffer stage on the device side, then that part of the device memory has to be accessible to the host. So that's what this allocate host buffer is about. The next option, CLMem copy host pointer. This is to initialize the buffer with data from referenced by the host pointer. So you're going to be seeing this copy host pointer coupled with a pointer to the host memory so that the OpenCL runtime knows how to get the initial data, which is pointed by the host pointer, and initialize the buffer with that data. The next three options, host write only, host read only, host no access, are to specify what kind of accesses are allowed by the host towards the memory object. When OpenCL creates a memory object, they are allocated in global memory space visible to all the devices in a context. So this is the goal of these memory objects. No matter where we physically allocate them, they need to be visible to all the devices in that context. In reality, the devices in a heterogeneous system may not share address spaces or may have physically separate memory units. So the OpenCL runtime has to create multiple copies of the data for each device. And that's the job of the memory management. Even in a shared memory space, the data may have duplicates in different cache hierarchy for the goal of improving the access efficiency. It is the OpenCL's relaxed consistent model that we do not allow multiple kernels to modify the objects at the same time. And reading data while the other kernel is modifying is undefined. Buffer is the memory object for passing large data structure to OpenCL kernels. And it's the very straightforward object that we commonly use in an OpenCL program. It is a contiguous sequence of elements similar to a C array. Although you don't have to have an array, you can have your own defined data structures in this 1D contiguous space. And based on the memory flags we just described, depends on which one you use, a host pointer can be optionally supplied if we want to initialize the buffer with the buffer already on the host side. Or even we can provide the storage on the host side for the buffer. By default, OpenCL does not specify the physical storage for the buffer allocated. It simply says the data is in global memory. So this is the OpenCL Create Buffer APIs called CL Create Buffer. It takes the context as the argument, and also you can supply the memory flags, and then you can specify the size of the buffer, and optionally you can provide a host pointer if you want to use the pointer as a way to find the initial value of the data. This buffer does not return an event, instead it returns an error code and of course the buffer object. Let's take a look at a concrete example. The following code is to create a buffer that is read-only and initialize it with data from a host array. Let's assume that context is a valid context. At the very beginning, we declare the error code, and then we define a array A that consists of 16 integers. The CL create buffer will use, in this case, CL memory read-only. That is to say that the kernel can only read from this memory object. Also, it uses the option CL mem use host pointer. So when it says use host pointer, this is to say that this buffer will be allocated on the host side at this time, and we will see how the devices will get the values when it attempts to read the buffer. And after that, we will do an error checking to see if this create buffer operation is successful or not. Now we're going to look at a different example. This case, we are creating and initializing a buffer in host memory. And the memory flags we're going to use here is CLMem copy host pointer, and coupled with this host pointer that points to some space on host memory. These two options is to ask the OpenCL runtime to create a new allocation for buffer and copy the data provided by the host pointer. Note that this API does not generate an event. We can assume data copy is complete when the API returns. So the API we're seeing here is we're going to use CL create buffer, assuming we have a valid context, and this is the memory flag we're going to use, copy host pointer, and data is assumed to be the host pointer that points to some space in the host memory. What we see in this diagram is that this is the context we are performing this buffer creation operation. And because this is a CL create buffer API, and the goal of this API call is to create a memory object that is called buffer, and this memory object is going to be in a global memory that is accessible to all the devices. because we have this CLMem copy host pointer flag, so what the OpenCL runtime does is to allocate a space that in fact resides in the CPU memory, the host memory. And because we supply the pointer data, so this API call actually then copies the data from this space pointed by data to the memory buffer just created. So we can see that we have implicitly a memory copy operation that's going to filling this new buffer with the data here. At this point, we actually don't have anything that's available in the GPU memory physically to be accessed by the compute units. So by the time the OpenCL kernel attempts to use this memory object, we will first set the kernel argument, then we use CL enqueue and derange kernel to instantiate the kernel, which will subsequently access the data. Only at this runtime, OpenCL will perform a DMA, direct memory access operation, to copy the actual data from the host memory to the device memory on the GPU side. And after that is done, the GPU kernel will then start reading the data from this GPU memory. So the point is the data transfer is implicit from the host to device prior to the kernel execution. After the computation is done, then we are going to copy the data back from the device to the host. So on the host side, you see another API, which is the CL enqueue read buffer, attempts to copy data from this memory object buff to the data buffer on the host. So at this point, there will be another direct memory access memory operation that copies the data from the GPU memory to the CPU memory. Or if it is FPGA, then it's the FPGA side memory unit. So that was the read operation to the buffer objects. For writing to buffers, the OpenCL also use command queues. So we can use command queues to read or write buffer data, to read or write data from a buffer or to a buffer. And in these cases, we're going to generate event for dependencies, or later can be specified as a blocking call. OpenCL use buffer read and write commands and generate events for dependencies, or we can specify blocking read or blocking write. Once the command completes, the host pointer can then be reused. So a programmer can think about that the data storage of the buffer object resides on the device after call completes, although this is not explicitly required by the OpenCL specification. This slide shows the details of the CL enqueue write buffer API call. As you can see that this API takes the command queue as the argument, and the buffer object, and a flag to indicating it's a blocking write or not a blocking write. And also it needs to specify the offset into the buffer to write to, and the number of bytes to be written to the buffer, and also the pointers to the source data where we want to copy the data from. The next three arguments are common for many other in-queue type of APIs, where this will specify the number of events to wait for and with the list of events, and also finally what events will be generated once this command finishes. We show you an example of writing buffer here. So again, we have a array of A on the host side. It consists of 16 integers, and we can use a simple for loop to initialize the values of this array A. Then we create a buffer, and we create a buffer as default both read and write operation, and we specify the size of the buffer. And here you can see that we do not have any other memory flags related to the host memory, so you can assume that this buffer is allocated on the device side. And then we want to initialize the buffer using CL in-queue write buffer. So we supply the command queue the buffer object we just created, and that is the destination of this write operation. And we use CL true to indicate that this is a blocking write. Offset is set as 0, and we provide the number of bytes to write, and then the host data. So this is the source of this memory write operation. So we're going to copy data from this buffer pointed by A to the memory object buffer on the device. And in this example, we do not wait on any events, and we do not generate an event. The following example shows that how we can create and initialize a buffer and then use it in a kernel without explicitly writing the buffer. This example is in fact what we saw at the beginning of this lecture, but we want to go over it again so that you can have a better understanding. First, we call CL create buffer with a memory flag CL mem copy host pointer coupled with this data pointing to somewhere in the memory, host memory. And what this API will do is to create a buffer on the host side. This is the new buffer created, and then copy the data from this buffer pointed by data to this newly created buffer. Even though this buffer is physically on the CPU memory, but conceptually we know that we have created this buffer in a global memory space of the OpenCL context, and this memory object should be visible or accessible to all the compute unit on the device side. In the next step, when we use set kernel argument and CL in-queue and the range kernel, we will know that the OpenCL will know that the buffer will be used by the kernel. So in this case, OpenCL tries to prepare the data by issuing direct memory accesses, copying the data from the host memory to the device memory. As a result, the buffer object is in fact pointing to some space in the device memory. So this implicit data transfer from the host to the device is done prior to kernel execution. The runtime, in fact, can also choose to have the device access the buffer directly from the host memory. As an alternative, we can use write buffer APIs to create a buffer directly and copy the data explicitly. So this is what we're going to do. So first, we use create buffer without specifying host related memory flags. So in this case, we actually create the buffer physically on the device side. So you will see the you see in this example as illustrated that the buffer object will point to a buffer allocated on the device side. And then we'll use CL enqueue write buffer to explicitly copy data from this host side buffer to this buffer object on the device side. Again, we use direct memory access to improve the data copy performance. After this is done, we actually have the buffer object pointing to the device memory, which now consists the initial data. We now have the buffer object pointing to the space on the device side, which consists of the actual initial data. Reading buffer APIs is a complementary call to writing a buffer, and it reads the buffer back to the host memory. This diagram assumes that the buffer data has been moved to the device by the runtime. So we already have the data here in this buffer on the device side. Then CL enqueue read buffer, which takes this buffer object as one of the arguments, and also the data, which is the destination where we want to read the data to. This API will cause the OpenCL runtime to actually copy the data from the device side to the host side. This is the details about the OpenCL read buffer API. It's called CL enqueue read buffer, which takes the queue as the first argument. It provides the source of the read, which is the buffer pointing to the device memory, a flag indicating it's a blocking read or a non-blocking read, and then an offset into the buffer to read. Actually, this is a typo here. Also the size of the data to be copied, and then the pointer to the destination. So this is a pointer to the host side memory. And again, the last three arguments are for the events, specifying whether this API call needs to wait for any events or generate any event. Now we're going to look at one example. So we have a buffer on the host side called return array, and we want to use this to store the final result when the kernel's finishing their computation. CL mem buffer is the output buffer that's on the device side, and then we assume that the kernels put the final results into this output buffer. CL event is to define an event that we're going to use in the read buffer API call. So between this declaration of the read event and this printf, we assume that there's some other code that will invoke the kernel, and it will generate result into the output buffer. Also, we assume that this return array are filled with all zeros. So when we get to this point, this printf will print out the values in the return array at index number 3. Because we initialize with all zeros, so we expect to see a printed here and then 0. Next line is the enqueue read buffer API. So we call this API by supplying the output buffer as the memory object we're going to read the data from, and we use here in this example CL false as the non-blocking read. So this read operation is non-blocking, and then we supply the number of bytes to be read, and then the destination, which is the return array that we want to fill out. And this API call generates a read event as the output. And after that, we have another two printfs. We have printf B and printf C, and between them, I have CL wait for event, and then we're going to wait for one event, that is the read event. So let's go over this Cre Buffer Api again. Because we have this non-blocking read, so this API in fact will go through, will finish no matter whether this read operation is indeed completed or not. What that implies is this printf at B, this return array is undeterministic because it may happen that the new data read from the output buffer are not updated to the return array before this printf is printed. And because we have this CL wait for event, this is to wait for this read operation to complete, because this read event is the output event of the CL in-queue read buffer. So the CL wait for event will actually block until this read buffer operation is completed. As a result, this printf C, this will for sure output the final data that's computed by the kernel. So to help you understand this, let me ask you this question. What if some kernel modifies output buffer which has different contents from the return array between the two printf calls? So this one here and here. So in this case, as I explained, because right now we are doing a non-blocking read, so the content in this return array at this point when we print the B is undeterministic. We do not know if this initial value 0 is going to be overwritten with the data from the output buffer. And because we have the CL wait for event, read event, this will block until this read buffer operation is completed. So the final printf will for sure print out the correct result from the output buffer. Now if we ask you the second question, let's change this blocking flag from CL false to CL true. So if we change this to CL true, that means we are making this in-queue read buffer as a blocking read. Blocking read will not return until this read operation is completed, which means that this printf will not be executed when this read buffer is in progress. So we can know that at this point, when we execute this printf B, for sure this read buffer operation has been completed. So we expect to see the correct output value printed out during this line, print B. Either way, this CL wait for events will get this CL read event, which is now completed. So we proceed on the final printf. So C will also print out the correct return value from the read operation. And you can guarantee that this print B and print C will output the same value if this is a blocking read. In OpenCL, there are some implications of asynchronous transfer. We can copy data from the host memory to the device memory, and from device memory back to the host memory. These changes to memory are not guaranteed to be visible. It is not guaranteed to be consistent until an event reports that the command's execution has finished. Such as in the previous example we saw, using events, we can indicate that the command's execution has indeed finished. If you transfer between host pointer and device buffer, you cannot reuse the data pointed by the host buffer until the event associated with the copying has finished. During a transfer between a host pointer and a device buffer, you have to pay attention that you cannot reuse the data pointed by the host pointer until the event associated with the copying has finished. And buffers associated with the context are not with the device. If you have multiple devices, OpenCL actually allows you to migrate memory objects between devices. It's different from reading and writing a buffer. This call guarantees that memory objects will be located on another device when the command completes. And you can use this API to migrate multiple memory objects. And this API is called CL enqueue migrate memory objects. We're not going to go into the details because in most of the cases we have one device, so we may not have a lot of need of this migrate objects in our course. Now let's talk about host accessible memory. When you create a memory object, you can use a flag to specify that this memory object should be created in a host accessible memory. Now, the host accessible memory is not necessary on the host. If on the device side you have a memory space that is accessible to the host, you can also assume that OpenCL can use that part of the memory. This host accessible flag requires that the allocation has to be mapped to a space that is accessible to the host. Oftentimes, if it is on the device side, this part of the memory should be mapped into this memory address space. CL mem allocate host buffer tells the runtime to create a buffer in the host accessible memory, whereas CL mem use host pointer is to tell the runtime that it's going to use the supplied host pointer as the storage for the buffer. And this will prevent the redundant copies of data, especially in the APU environment. We're going to briefly talk about APU environment in a later slide. The CL memory copy host pointer together with this CL mem allocate host pointer is to say that where or how we're going to find the initial data to put into the buffer, to initialize the buffer. For both the allocate host pointer and the used host pointer, it is reasonable to assume that the implementations will have the device access the buffer from the host memory across the PCIe bus. This is very common, especially to improve the memory performance by using so-called zero copy method. So it essentially use a space that is on the host side or on the device side and use memory mapping so that both can access that part of the memory. This is not explicitly required by the OpenCL specification, so depends on the actual device. Vendors may have different implementation. Host accessible memory has a very interesting implication. let's say for example, AMD specific treatment of these flags, they leverage APUs, which is a tightly integrated CPU and GPU architecture. These two processors share memory space. So this CLMEM allocate host pointer and CLMEM use host pointer will be essentially the same, because if the device supports virtual memory, which is the shared memory space between the CPU and GPU, the storage will create as pinned host memory, and they will be accessed using zero copy. If no such virtual memory is enabled or available, then storage will be allocated on the device side. Also, there's a new flag called Use Persistent Memory Amd. This is a vendor-specific extension. Will ensure that the access to this memory object from the host will be directly to the device memory. So there will be no copies on the host side. When you use these memory flags to store data, you want to make sure that you understand the performance implications of your choices. We can use one other technique called mapping to make it easier to access data on the device. OpenCL provides such a mechanism for the host to access the data without going through explicit read and write API calls, and also to avoid data copying. And these APIs are called CL-INQ map buffer, and on the other hand is unmap memory object. When we use CL-INQ map buffer, what the OpenCL runtime attempts to do is to provide a pointer to the host side, and so that the host can use this valid pointer in the host memory space to access the data in the device. And it's similar to the read-writing to the buffers. Let me show you an example. So first, we use CL Cre Buffer to create a buffer space memory object on the device side. So this buffer object points to some space on the device memory. And this CL-INQ map buffer API call will take this buffer as an argument. And this API call will return a mapped buffer. Note that this mapped buffer is just a memory pointer on the host side. As if you have, let's say you do a malloc on the host side, and that returns a valid pointer. So this pointer can be then used in a similar way as you create such a pointer using malloc. So all the following operations that performed on this mapped buffer will in fact take place in the device memory. But to the programs on the host side, it sees this mapped buffer as just a regular pointer in the host memory. In other words, this buffer, this memory object, is mapped to the host's address space. Once the necessary memory copy operation is done, or any computation is done, we can then use CL-INQ unmapped memory object to release this mapping. So as a result, there will be no valid pointer from the host memory space pointing to the device buffer. In new OpenCL 2.0 specification, there's a new concept called shared virtual memory. Shared virtual memory is to extend the global memory to the host memory region. The major benefit is to allow the addressing to share the host in all devices. More concretely, we want the device to be able to access the data that's on the host and may not be in the sequential order. For example, we can pass pointers-based data structure as argument to kernels. Pointer-based data structures are, for example, linked lists, trees, graphs, and kernel can then operate on such linked list. Without having this shared virtual memory, the kernel cannot work on such linked list spread across the memory, because in that case, the pointers given to the kernel is invalid for the kernel to access, because the pointers are addresses in the host memory space. With this shared virtual memory, the kernels can use these pointers of the host memory space to find the right data. There are some detailed options of shared virtual memory at different granularities, and then their OpenCL object is slightly different, and the allocation methods and consistency model is slightly different. And if you're interested, you can refer to page 6.1 on page 159. This is an example of doing shared virtual memory allocation. It takes the context and the first argument with possibly some flags to indicating the granularity and the size and the alignment. This SVM alloc will return a non-null if the allocation of the shared memory is successful. And after that buffer is used, we can then free the buffer. Images are different in buffer in several ways. They are opaque data types that cannot be viewed directly through pointers. And these are multi-dimensional structures and have limited range of types for graphics data, rather than being free to implement any arbitrary data structures. Image objects is to offer access to special function hardware on graphics processors or FPGAs to support highly efficient access to image data. There are specific filtering operations that can allow efficient transformation of the image data based on the pixels. Pipes are new memory objects in OpenCL 2.0. They are essentially first in, first out FIFO type of structure. They are primarily used to pass data from one kernel to another kernel, so that within a device, two kernels can share a region of memory and then guarantee the protection of this shared state. This implies that devices that support pipes must support atomic operations, because these FIFO operations have to be atomic. Also must have a memory consistent model supports acquire and release semantics. And they can use specialized memory different from the main memory. And currently we do not allow host side operation on pipes.